For more videos like this for Operations Management 386, you can check out Sarai Studies, link is in the description box below. Denim World, a local shop, makes shirts and pants using two resources: hours of labor, so the hours that the employees work, and yards of denim. The shop has a maximum of 90 yards of denim and 40 hours of labor available each day. Each shirt requires 3 yards of denim and 1 hour of labor, while each pair of pants requires 4 yards of denim and 2 hours of labor. The profit from each shirt, so how much you make when you sell a shirt, is $40, and how much you make when you sell a pant is $70. The shop wants to know how many shirts and pants they need to make every day to maximize profit. Our goal is to translate this word problem into a model, and there are 3 steps to do that. First, we define variables, then constraints, and then finally our objective function. But realistically, once we read a problem, we ask ourselves, what is our goal? What is our objective? So we say, okay, let's try to define our objective. Our objective is to maximize profit. So no matter if you're dealing with profit or cost, whatever you're trying to maximize or minimize, we call Z. So in this case, Z is our profit, and we are trying to maximize that profit. So we will say max Z. And then you ask yourself, well, what does profit depend on? It depends on the number of shirts and pants that I sell. And in order to sell them, I have to produce them. So again, my profit depends on the number of shirts that I sell times however much I make when I sell those shirts. So I make $40 for every shirt that I sell, plus the number of pants that I sell times however much I gain for every pant that I sell, so 70. And the objective is to determine how many shirts and how many pants to produce so that I get the maximum profit, Z. But the reason that the first step is to define your variables is because we can write these two things as variables. So we can let x1 be equal to the number of shirts and x2 be equal to the number of pants. So now we can replace this number of shirts with x1 and this number of pants with x2, making this a very nice and compact objective function. Now you want to define your constraints. Your constraints are restrictions, so your problem tells you the restrictions. Here, it says that the shop has a maximum of 90 yards of denim and 40 hours available each day. So the restrictions are on our resources, on the hours of labor and the yards of denim. So I always like to define what is being restricted. So yards of denim and labor hours are being restricted. Now with your constraints or your restrictions, there are always 3 parts. Here, I like to write the restriction. So in this case, for the yards of denim, I have a maximum of 90 yards of denim. So 90. So this is how much you can use. And this one is how much you do use. So how many yards of denim you do use has to be less than or equal to how much you can use, which is 90 yards of denim. So what goes here is your inequality sign. Now, how do you define how much you do use? Well, it tells you. Each shirt requires 3 yards of denim. So for each shirt that you make, so x1, you're going to use 3 yards of denim. And for each pant that you make, it requires 4 yards of denim. That's going to represent how much of denim you do use, and that should always be less than or equal to how much you can use, how much you're restricted in using, because there's only 90 yards of denim available each day. Similarly, for hours of labor, how much can we use each day? Well, we are restricted to using only 40 hours of labor. So that is how much we can use each day. And so however much we do use has to be less than or equal to 40. How do we define how many hours of labor we use? It depends on how many shirts and how many pants we're making, plus however many hours we need when we make a shirt. And they tell us that making a shirt requires 1 hour of labor. So that's 1. And making a pant requires 2 hours of labor. So that's 2. But you may think you're done with your constraints, but you're not. Think about it. You're trying to determine how many shirts and how many pants to produce daily to maximize profit. In other words, you're trying to find x1 and x2, but what can x1 and x2 not be? It can't be negative, because you can't be like, yeah, I'm going to produce -1 shirts today or -5 pants. So another constraint on what x1 and x2 can be is that they have to be greater than or equal to 0. You can make 0 shirts and 0 pants. You just can't make negative amount of shirts and pants. And these are 2 constraints, but you can put them all in one by saying x1, x2 greater than or equal to 0. So again, this is a constraint on what x1 and x2 can be. And even though we have constraints on the yards of denim and labor hours, they are still constraints on what x1 and x2 can be, because x1 and x2 depend on the resources used to make them. So yards of denim and labor hours. So if these are restricted, then these are are also restricted. Now we have everything that we need to set up our model. So you want to do a little box, you put your objective function right there, and then you put your constraints, and you want to say subject to. What that means is that this function is subject to, it's constrained by this constraint, this constraint, and this constraint. Now we have our model set up and we can go ahead and start solving it. You first want to start by plotting the constraints. So you want to take your constraints. You don't include this one because this one just means, hey, we're only looking at the first quadrant because that's when x1 and x2, x and y are greater than or equal to 0 at the same time. So you want to focus on these constraints. And you just want to make them equal. Just get rid of the inequality for now. And just try to plot these lines. How do you plot a line? Well, think about a line. What do you know about a line? Well, a line has points. So if you could find 2 points on that line, then you can plot it. So for each constraint, we just let x1 be equal to 0. So if x1 is equal to 0, then this goes away, and we're just left with this. And then to solve for x2, we would divide by 4 on each side, and we get that x2 is equal to 90 divided by 4, which if you use a calculator is 22.5. So our first point is x1 is 0, and x2 is 22.5. So this is only 1 point for this line. We need 2 points. So we let x2 be equal to 0. So if x2 is equal to 0, this cancels out and we're left with 3x1 is equal to 90. So to get x1, we divide by 3 on both sides, and we get that x1 is equal to 90 over 3, which is equal to 30. So our second point is x1 is 30 and x2 is 0. So on our graph, and the reason we are only focusing on the first quadrant and not have a graph that looks like this with all quadrants is because of this constraint. x1 and x2 can only be greater than or equal to 0, can only be positive. So 30, 0 would be somewhere around here, and 0, 22.5 would be somewhere around here. And there we go, we managed to plot this line. Now let's try the same for the second constraint. So we let x1 equal 0. So this 0 cancels this out. We're just left with this. Divide by 2 on both sides. We get that x2 is equal to 20. So our first point is 0, 20. Then to get our second point, we let x2 be equal to 0. If x2 is 0, this cancels out. We're left with 1x1 is equal to 40. So x1 is equal to 40. So x1 is 40, x2 is 0. Now we can plot these 2 points. So 0, 20 is right about here, and 40, 0 would be right about here. So we managed to plot this line. So what we're trying to do is plot the constraints, but there are 2 parts in plotting the constraint. The line themselves, which is why we remove the inequality sign and just focus on the equal sign, so it's easy for us to just find 2 points and plot the lines. But the constraints also have an inequality sign, so how do we take care of that? Well, when we have an inequality sign, it's just about shading. We need to shade our constraints. What do I mean? Well, if we have this constraint, the question is, do we shade below it or do we shade above it? How can you tell? Well, I'll tell you how to not tell, and that's by looking at the sign. The sign of the constraint does not tell you where to shade. Just because it's less than or equal to does not mean you're going to shade below it. What you have to do is pick something called a reference point. Now it can be any point, but I suggest you just always pick 0, 0 because it's the easiest. And all you're going to do is take your constraints and plug your reference point into the constraint. 0 for x1 and 0 for x2. That makes this whole thing 0. And then we have less than or equal to 90. Then you ask yourself, is this true? Is 0 less than or equal to 90? Does it satisfy this inequality? Yes. So what does that mean? That means that you are going to shade the area that contains your reference point. In this case, it's 0, 0. So for this constraint, the question is, are we shading below or above? Well, this tells me I want to shade the area that contains 0, 0, and that's below the line, so I'm going to shade below it. Now we do the same here. We plug in 0, 0. That makes this whole thing 0. Is 0 less than or equal to 40? Yes, so we want to shade the area that contains our reference point 0, 0. So are we shading above or below? Which one contains 0, 0? The area below. So this right here. If our reference point did not satisfy this constraint, then we would not shade the area that contains that reference point. For example, if it was something like this instead, then 0 is not greater than or equal to 90. So for this constraint, we would not shade the area that includes 0, 0. So we would shade above the constraint. We would not shade below. And let me actually label these points as well. This is 40, 0, and this is 0, 20. Now step 3 is to determine our feasible area or region, and that is simply where all of the colors intersect. So where the yellow and the purple intersect are right over here. because here there's no purple and here there's no yellow. So we simply just get rid of all of that. We call this our feasible region. Feasible because if you pick any point in this area, in this region, it will satisfy all of your constraints. An infeasible solution would be one over here. Even though it's on this yellow, it does not satisfy this purple constraint. So it would be infeasible, or a point right over here as well. Remember, our goal is to find our optimal point, our optimal solution. So you may be confused like, okay, why am I plotting a graph? How does that help me? Well, the reason we plotted the graph is to find the feasible region. But then, okay, why does the feasible region matter to me? Well, there's this theorem called the fundamental theorem of linear programming that says all things linear, so we have to be in the linear world, your optimal point will be one of the corner points, so one of these points in your feasible region, which is this region right over here. Which brings us to our fourth step, which is to determine the corner points and test to see which of the points, because remember, they are x1 and x2, which x1 and x2 will give us the largest z our profit. Why largest? Because this is a maximization problem. So this is a corner point. I'm going to call this point A. We'll call this point B, point C, and point D. So point A is 0, 20, point B is 0, 0, point C we don't know yet, and point D is 30, 0. Now, how did we find point C? Because we need to find it. Well, if we go back to our original graph, this is point C, this is point C. So what can you say about point C looking at the original graph? Well, it's the intersection between these two lines. So you just have to find the intersection between these two lines and you get point C. This is just a system of equations. You can either use substitution method, elimination method, or if you've taken linear algebra, you can do row reduction. I'm going to do elimination method. So all you want to do is focus on getting rid of one of the variables. So let's say I want to get rid of this 3. Well, I can take a look at this one and ask myself, how can I get this plus this to give me 0? Well, if this was -3, then when I add this plus this, it will give me 0. But whatever I do to one thing, I have to do to the rest of them. So I'll have to do -3 times this whole thing. This becomes -3. This becomes -6. This becomes -120. Then I can add the constants. 3 minus 3, 0. x1 plus 6 minus 4, 2, but it's a -2. x2 equal to 90 minus 120, -30. 0 goes away. I can divide by -2 on both sides, and I'm left with x2 is equal to -30 divided by -2, and we know that is positive 15. Now that we know one of the values, we can go back, plug it into an equation. I'm actually going to bring back the one that was here. It was 1x1 plus 2x2 is equal to 40, because it's the easiest because it has a 1, and I'm just going to plug in 15 for x2, so that gives me 30. So -30 minus 30, this goes away. This becomes a 10. So I'm left with x1 is equal to 10. So point C is 10, 15. 10, 15. Now, to test to see which one of these points is going to give us an optimal solution, we will need our objective function. So I'm going to copy it, move it over here. So z is equal to 40 times, in this case, x1 is 0, plus 70 times x2 is 20. This becomes 0. 70 times 20 is 1,400. So remember, z is profit. So that means that when we produce 0 shirts and 20 pants, we make $1,400. Remember, this is x1, x2. x1 represents the number of shirts. x2 represents the number of pants. That's what these points are telling us. These are all feasible points. They are points that satisfy all of these constraints. Now I'm going to try again. This time 40 times 0 plus 70 times 0 is equal to, well, $0. For this one, 40 times 10 plus 70 times 15 is equal to, well, this is 400, plus 70 times 15 is 1050. That gives us 1,450. And finally, for this point, it's 40 times 30 plus 70 times 0, and that is equal to just 40 times 30, which is 1,200, because this goes away. Now we're looking for the largest z. The largest z is this one. So our optimal solution is $1,450 as a profit. And we can only gain that if we make 10 shirts and 15 pants. So the way that we write our conclusion is a little box, and we say our optimal x1, so the optimal number of shirts that we should make in a day to maximize profit, is equal to 10. The optimal, so the star stands for optimal, number of pants that I should produce in a day to make the maximum amount of profit is 15. And my optimal solution, my optimal amount of profit, my max amount of profit is equal to 1,450. So if we go back to the problem, we determined the number of shirts and the number of pants to produce daily to maximize Z, or profit, and that was 10 shirts, 15 pants, and the maximum profit is 1,450. So the point that gave us our optimal profit was point C. So our theorem holds true that one of our corner points, and I should say one or more, because it could be that you could have another point that gives you the same value like this, and then you would have two optimal points, but the same optimal solution. So keep that in mind, but the point is point C, no pun intended, is our optimal point, and it is one of the corner points in our feasible region. Now in the next video, we'll talk about something called slack and surplus variables. See you in the next.